What you do with those is gather data in some way and then analyze it to see if you are within an expected ratio. And, you know, we can think about expected ratios lots of ways. I always start my kids thinking about expected ratios with flipping coins. Okay, and so if we've got a chi-square formula, we want to go after deviations and expected. You can't do chi-square unless you know what you expect. Okay, so a 3-to-1 ratio in Mendelian ratio, in a Mendelian ratio, you have an expectation, or a 9-to-3 or 3-to-1, or if you flip coins, what do you expect to happen? 50-50, right? So we can use that as a model to understand actually not only a chi-square formula, but the importance of gathering lots of data. So chi-square is equal to the sum of the deviation squared over the expected. And what I like about this particular activity, we do it with pieces of yarn that we go out and distribute outside, different colors of yarn, and they're worms, and the kids go pick them, and then we say, oh, there's some worms that got picked and some that didn't, and you know, it's kind of elaborate. You have a nice description of it in that activity. But this is the data sheet that goes with it, and it follows the parts of the formula. So what you do, the kids record a color, it might be red yarn, and they have how many they observe. So we actually, you know, are gathering data and we observe something. Let's do heads and tails, because you can observe that. Let's flip a coin 10 times and say you get 7 heads and 3 tails. That's what you observe. Okay? So you would put over here, okay, here's heads, here's tails. So we only have 2 options. We observed 7 and 3. Okay? What did we expect though? 5 and 5. How much did we deviate? What's our observed minus expected? How much did we deviate? 2.
2.
And 2. And what's our deviation squared? 4 and 4. I'm going to do it again over here so it's a little bit bigger. And then what we have is our deviation squared over the expected. So we have 4 over 5 plus 4 over 5, because it's the sum of the deviation squared over expected. Let me do it here so the number's a little bit bigger.
Can you explain why the sum part?
That is the formula. It was written as the formula to do the statistical analysis.
No, but I mean, why twice? Why not 3 times or 7 times? Why?
Okay, I think it'll be clear here. Yeah. This is what we observed, 7 and 3. We expected 5 and 5. We deviated 2 and 2. Our deviation squared is 4 and 4. And our deviation squared over the expected is 4 over 5 and 4 over 5. Okay, can everybody see that? And what chi-square is the sum of the deviation squared over the expected. So I would have to add 4 over 5 plus 4 over 5. And what I get is 8 over 5. Everybody got it? Okay. And then what I want to do is get a whole number from that, because you can't do chi-square with a fraction. You need, you know, a whole number or decimal to do that. So if I have 8 over 5, what's that whole number?
Whole number?
8 divided by 5, or what is the number? 1.6. Yeah.
I needed a calculator if you will.
I needed chocolate to do it. Okay. So now we have a number that is the sum of the deviation squared over the expected. And we can use our table to tell us, is this within the realm of expected results or not? Chi-square is used to say, we saw something, we expected something. Was there something interfering, or are those good and relevant data? that's what this is used for. What we start with is the degrees of freedom on it. And really what that means is if you see one thing, you make an observation, what else could it be? So with heads and tails, if I see heads, what else could it be? Tails. So I actually have 1 degree of freedom.
Can you give another example?
Yes, if I'm out distributing yarn outside and I put 6 colors out there, I pick up a red one, what else could it be? 5 other colors.
So that would be 5 degrees.
That would be 5 degrees of freedom. And basically, it works into the formula to show a distribution, okay? So I have 1 degree of freedom, and I grow, my number is 1.6. So I go across and I go, oh, it's right here. It's not up to 3.8. It's less than that, so it's on this side, right? And if I go down, what I have is a table that tells me that random chance hypothesis is acceptable. So if I flip a coin 10 times and I get 7 heads and 3 tails, I should accept that data as random chance. And the number is significant actually here. When you get to probability of 5%, we throw the data out. Or we say, let's find another explanation. And that's in a general scientific experiment. If they were doing drug tests or whatever, for medical things, it wouldn't be 5%, it'd be a lot higher than that, acceptable data. But with a chi-square analysis, we're just looking for that 5%. And that's because of this. Bell curves, and actually those numbers on those far ends of that distribution, if it's here or here, it basically adds up to the 5%. It happens so rarely that we just can't accept it as part of a scientific experiment. I tell my kids, I want you to see enough to recognize the ends of a bell curve, because then you can tell if you're within your realm of probability or not. Well, let's see what happens though. Same ratio. Let's flip it 100 times. Because we just said 7 and 3 is acceptable, right? With 10 flips. But what if you flip 100 times and you get 70 and 30? Same ratio. We'll do the math. 70, 30. What did we expect? 50, 50. How much did it deviate? 20, 20. Here's where the clicker is. Deviation squared. Okay? So what is 20 squared? 400. 400. Okay? So now what we have is 400 over 50. 400 over 50. Our number is 800 over 50. So what have we done to the sum of the deviation squared over the expected? That number isn't 1.6 anymore, it's 16. Okay? So now when we go up here and we say we have 1 degree of freedom, and if we go over and see the number 16, we're off the charts. The probability is, less than 1 out of 1,000 for that to occur. And so what we would say is something has affected, something's, in this experiment is interfering with our random chance hypothesis. We can no longer accept our null hypothesis, which is basically that there isn't anything significant interfering with our experiment. And if a scientist saw that, what would they do next? I mean, what do you do if you say random chance hypothesis is not acceptable anymore? What could you do?
Some of the threads were green and they were in grass.
Pardon me?
If some of the threads were green and they were in grass and the students didn't see them to collect them.
Sure, if it's the woolly worm lab, I put 20 colors out there, and I make a little key. And the kids come in and maybe they found 19 of the red ones, and they haven't found any of the skinny little brown thread that I put out there. They go, "You kidding me? There were some of those out there?" And I said, "Wait till next year. Those things are all out there reproducing." Hey, I put a sweater with the yarn that's out there. A null, well, it's really clear with this right here, I think, this statement. Your random chance hypothesis is not acceptable, or your random chance hypothesis is acceptable. So we would accept our null hypothesis here.
Well,
That
what's
it's
the
random
null
chance.
mean? Just
The-
our
I think
price
it
of
means the negative, basically. The way I look at it is like no, there's a null. There's nothing is really interfering with the data that you're collecting.
Okay.
Nothing significant.
So in that chart, you can replace random chance with null.
Yes, you could. Random chance means null. I like the kids to think about random chance, though. Yes. Yes.
So it's within the.
Well, this is, for chi-square definitions, what they say is if something happened, could happen 5% of the time, or more than that, we would accept that this is just variation, just normal variation. If it happened less than that, you know, if it happened only 1% of the time, what a scientist would say is there's either another explanation, something's interfered, and I mean, think about it like with Mendelian ratios. Maybe you expect a 3-to-1 ratio and you get a 2-to-1 ratio. And you because you had enough flies, you calculate it all out, and it's not acceptable. And so you go, well, what's going on? Well, something might be maybe there was a lethal gene involved, or maybe there's another explanation of something. With the coins, if you got 70 and 30, you probably look at the coin. Is it weighted on one side? Or is there something's interfered with that random chance hypothesis? It's a very useful tool in terms of the kinds of data that we collect in biology studies. Yes?
What did you say about the bunnies?
Oh, I'm sorry.
That's what I wanted to.
The 5%, when you do a standard deviation curve, this is at the 2.5 and this is at the 2.5 in terms of distribution. Yeah, it's just a distribution. And what you'd say is, you know, if you saw something so rarely, then there might be something else interfering.